Good morning, everyone, and thank you for showing up for your learning today. We are looking at our exponential review. So we have the package, and we're going to get her done. So let's take a look at these situations. We want to create equations that model these following situations. We might even use these equations to answer some questions. So here we go. There's a government, and they want more zebras. Because, who wouldn't? Oh, no, it's not zebras, it's giraffes. And so they start this aggressive breeding program now in 2021. And that results in the population of giraffes starting to grow by 23% per year. Is that a successful program or an unsuccessful program? That's a wildly successful program. Yeah, so here's what we need. We need to create an equation A of t. We might have even said this is g of t. The number of giraffes is a function of time, and that's going to be equal to the initial value, the initial number of giraffes, multiplied by the growth factor. Growth factor is made out of this percentage, but it is not that percentage. And then we're going to raise that to the power t. Okay? Here our v, this is our v, 2,100 giraffes is our v, and our b is this as a decimal plus 1. That's our growth factor. That's 123%. That's how many giraffes are going to be there next year. So the a of t is going to be 2,400 multiplied by 1.23 raised to the power t. There, done, final answer. That's all we've been asked to do there, is just create me a nice exponential function that will predict the number of giraffes in successive years. Now, this is a different situation. This is an example of exponential growth. Pretty soon, we've got so many giraffes that we don't know what to do with them all. This is different. This is exponential decay. So there's a group of aliens. They're out there. They begin an aggressive abduction program. Oh, sorry, if anyone has an alien abduction experience and that was triggering, I do apologize for making a reference to alien abductions. So, yeah, I should give the trigger warning ahead, shouldn't I? Yeah. They're removing 12% of the city's inhabitants per month. That means there's 12% less each month. So this growth factor is going to be 1 minus that as a decimal. Okay, that's their growth factor. B is equal to 0.88, which is a number that you would like quite a lot if you were superstitious in the Chinese way. So the population is going to be a function of time. Notice I could have used A of t, but instead I chose P of t because reasons. And it's going to be the initial value, 55,000 people, multiplied by the growth factor, raised to the power time. Done. That's the equation. How long will it take for the population to be 8,000? So, at least 3 years. Yeah, it's going to be a little more than 3 years, right? It's going to take a few rounds of. Oh, this is per month. Time is a month. Yeah, because they can reduce the population quite aggressively because they've got a lot of UFOs. Yeah, they're alien. They do what they want. Okay, so here, 8,000 is the desired population. That's equal to 55,000 multiplied by. I still have a little bit of Yoda going on with my voice. 88 to some power t. I don't know, but this is one equation, one unknown, can be solved. Yes, we can solve it with logs, but you're going to solve it by guess and check because curriculum. So here, first, simplify it as much as you can, makes it easier. I'm going to divide by 55,000. That's going to isolate this growth factor, and it's going to isolate the exponent term. Okay, and that's going to be equal to this divided by 55,000. And that's going to be 8 over 55. 8 over 55 can't reduce, so let's get a decimal here. Decimal. 8 divided by 55. Mr. Jennings, why didn't you do 8,000 divided by 55,000? Oh, come on, I can cancel that. Okay, so 14.5. 14.5%. So that's going to round up to, we can do 15% here. We can round to the nearest percent, sure. Okay. So let's do that. So it's 0.15. 0.15 is equal to 0.88 raised to some power t. Okay, if I multiply this by itself enough, I'll get down to here. Let's find out how much. 0.88. Here's a trick. Put it in your memory. Raise that to the power 12 months. Too big.
Bit higher. 15. Bit higher.
15 months.
15.08128.606.
Wait, so you just, for that one, when we get to 0.15 equals like that, you just have to guess? Yeah.
That's a 2. This is 1/2 raised to t divided by the half-life. So here we divide by the half-life to create our exponent. And then, so that's our function. This predicts how much of this, oh my goodness, will be available after a certain amount of time. So how much will be present after 21 seconds? Plug it in. Some of you have been saying that your calculators are not cooperating. So put your exponents in brackets. That will force your calculator to do the proper BEDMAS. There, 7.8 grams. Notice up here, if you can see, I can't zoom in on it, but this is 144 times the base of my exponent, a half, raised to the power, in brackets, put the power.
Does it just have to be like one decimal place? Does it just need to be like one decimal place unless you ask for different? Like 7.8.
Okay, let's keep going. Oh, that's much better. So, if I want to know how long that'll be for there to be 10% left, what's 10% of 144? So I could do it this way. I could say the amount will be 14.4 is equal to 144 multiplied by 1/2 to the t over 5. Okay, I could do it that way.
Why'd you do 14.4?
Because I said, how long will it take for there to be 10% left? There's an easier way to set this up. When I divide by 144, both sides, I'm going to get 0.1. I'm going to get 10% is equal to 1/2 multiplied by t over 5. I would just jump right to this line here. You see how I can jump to just that line there? Doesn't matter what the initial value is. I want to know when is it going to be 10% of that. So if I said there's 8 million grams of unobtainium, then when there's 10% left, there would be 800,000. When I divide both sides by 8 million, I get 0.1 on that side. This term here is telling me what percent of this is present.
So if it was like 20%, you could just write.
Actually, 0.2 there is equal to this. Yeah, be the same.
And for any for any number, it would still be the same.
Yeah. I could even say, when was there 200%? That would be going back in time. When was it 200%? Because this declined from some point. We measure it at time 0, and then it keeps half-lifing. Michaela? Oh, 10%. 10% as a decimal, 0.1. I divide both sides by 144, I get 0.1. Hayden?
Is unobtainium a real thing, or just make it up?
It's from the movie franchise Avatar. Well, it's not a franchise yet because they haven't come out with the second one, but it's coming. Anyone seen Avatar?
Yeah.
It's like a very forgettable movie. I don't know. The only thing I remember about it is they're looking for unobtainium. And I remember that because it's like, sounds so cool until you think about it. And it's like, wow, that's so lame.
What was it? Avatar, like, can you not get it? Like,
Not the Airbender.
the highest grossing movie of all time.
Yeah. The James Cameron movie. Yeah.
Can you not get it? Is that why it's called unobtainium?
Right, but you can get it. So why is it called unobtainium? It's lame. Okay, this one again, just a guess and check question. Create a table of values and work it out, and that'll be fine. If I wanted to simplify this first, it would be like this. This is a big if. This actually relates to this question here. I'm going to transform this function around a little bit just with my exponent laws. 0.1 is equal to 1 over 2 raised to the 1 over 5 raised to the t.
Wait, 1 over 5?
T over 5, that's my multiplication of power of a power rule, backwards.
Right, yeah.
See the power of a power rule backwards? I can decompose these fractions this way, and I can evaluate this. This is equal to 1 over the 5th root of 2 raised to the power t. I could punch this on my calculator, and then I have something a little simpler to pound values of t with. Might simplify your guess and check. You can absolutely guess and check here and find an adequate solution.
Is that okay? Like, would we get full marks for that if we got it?
Yeah. To the nearest, I think I'm looking for the nearest one there. Nearest second is fine.
16.59.
Wait, so
Great.
What did you say?
Did you?
15.59.
No, we didn't find an answer. Here, let's take a look at a table of values, what it's going to be like. I know that t over 5, if one half, if I multiply that by itself once, is 2.5. If I multiply it twice, it's 1.125. If I multiply it 3 times, it's going to be below that. So I know that the answer is going to be between 10 and 15. Between 10 and 15.
It's just over 15.
Is it just over 15?
16.6.
Oh, yes, that's right. That's right. Yes, I skipped one. Yeah, I skipped a power of 2 in my mental math. Just like Mr. Kujala made a mental math error and asked me to find his mistake, but couldn't show me his mental math. It's like, I don't know, everything looks correct.
Is this another one where you're guessing?
At this level, you can use logs for this one to find an exact answer, or you could graph and find a very, very, very precise answer with decimals.
But on the test,
On the test, it's guess and check. And I give you guess and checky questions that are not punishing you for guessing and checking. Let's take a look at this one. Camden had a lovely idea. He said, Mr. Jennings, I noticed that you have a negative power on top and a negative power on the bottom. Can I just flip the whole thing? Yeah, you can here. That's cool. You could take this one. Let's just draw our fraction line first. This is to a negative 2, so let's put it to the bottom. X squared times y to the 3 to the 2. It's no longer to the negative 2 because I changed its its position in the fraction. This one, same story. Cool. That works. Now let's keep going. Multiply these in. So that's going to be equal to 3 to the 3 is 27. Notice 3 to the negative 3 on the bottom, flip to the top of the fraction 27. He's useless. Move him over here. Okay, and x to the negative 4 to the 3, that's x to the negative 12. Y to the 3 to the 3 is y to the 9. Aiden?
So when you're flipping them from the bottom to the top or vice versa, you only switch the sign of the exponent outside brackets. You don't do the ones inside.
The one inside, it's also going to flip, but I'll have to flip it later.
Okay.
I could have flipped it there because I'm good at this stuff. I don't want to confuse people. Yeah, the ones that's on the outside, do that first. And another rule here is you want to do exponents first before you do multiplication and stuff like that. But you also want to do brackets first. This one is like the first one to do out here. This one's the first one to do. So you can take care of those negatives just by flipping. And then if Aiden, I had something like a 3 here, multiplying this bracket, that would not flip down with the negative. It would stay out. Tricky, eh? So now I can do my all of my other simplification. This x to the negative 12, it's x to the negative 12 subtract 4. So that's x to the negative 16. But I want to write this with a positive exponent. So I could say 27, that stays on the top. Y to the 9 over y to the 6, that's y to the 9 minus 6. That's y to the 3. Divided by x to the 16.
So
Negative 12, subtract 4, x to the negative 16, flip it down to the bottom, x to the 16.
so when you originally do it, all of before you flip make the x to the 16 down, it would all be on the top to start, and then you have to bring that down. Like
You could write the whole thing on the top. You just have some negative exponents.
when you do like something subtract something, and you get your answer, does it automatically stay on the top or on the bottom?
It's wherever you were doing it, right?
So like if you did negative 12 subtract 4, and or like say
Yeah,
it's like
negative 12 subtract 4. That's x to the negative 16. Let's start on the top.
Say it was 12 subtract 4.
Say this was positive 12?
Yeah.
Then it would be x to the positive 8.
Would that
Stay on
would
top
that be on the top?
because positive is on top.
Can you scroll up a little bit?
How's that? Shows you what you need.
How did you get negative 12?
Oh, x to the negative 4 to the 3. Power of a power, I multiply.
It flips though, because that one's on the bottom. So wouldn't it be positive 12, negative?
Look at it here, Camden. If I did it here, x to the negative 4 to the negative 3, that'd be x to the negative 12. Sorry, that'd be x to the positive 12, but on the bottom. So that, now, but here it came onto the top because you wanted me to flip it up here.
So then wouldn't it flip sides when it goes over? So it'll be
I did this one, Camden. I didn't do that one. I'm not ready to do that one yet because I have to evaluate it to this exponent first.
I got when I put it in photomath, it gave a different. It gave x equals 16 on the top and y equals 3 on the bottom. Because it flips the signs when it goes, like on this, it flips the signs. And like that's how I did it.
You don't have the same question there.
It's not?
No. It's not the same question. I don't think.
Yeah.
See?
I just, because I took the picture of it before, because I flipped it on here before I took the picture on it. Oh, so maybe that's why.
Maybe.
Yeah, that might be the problem.
Max?
What is it like in the negative 4 when you flip it over 9?
Here, this one?
Switch sides, yeah.
Oh, because I'm switching that sign. So that moves all this up. And then later I could evaluate that one. It's going to flip again. It's a little bit like a light bulb question, right? It's on, off, and you have to calculate accurately how many times it's been flipped on, off, on, off. But now instead of going positive, negative, it's going top of the fraction, bottom of the fraction. So another way to do it, Max, would just be to multiply these in. So let me do it another way in another color. Okay, we're getting some interest in this question, so let's look at it another way. This is equal to, multiply these in, x to the negative 4, y to the negative 6 on top. Okay, divided by 3 to the negative 3, that's going to be 1 over 27. X to the negative 4 to the negative 3, that's to the x to the 12. Y to the 3 to the negative 3, that's y to the negative 9. Okay? Now, I'm not going to flip anything. I'm just going to go to the next line. X to the negative 4, subtract 12. That's going to be x to the negative 16. Y to the negative 6, subtract negative 9. That's y to the positive 3. Negative 6, subtract negative 9. Negative 6 plus 9, 3. Okay. This 1 over 27 dividing by a fraction is the same as flip and multiply, so I'm going to put this 27 on top. Okay. And then x to the 12, y to the negative 9, we already did that. So we have the same thing we have here. We just need to now move this x to the 16 down. And then it's this. Same thing. Okay? Okay, let's keep going. Yeah. Here's a doozy. Let's take a look at this one. 16x to the 4 over 81 y to the negative 8. I have some extra brackets here. They're not incorrect, but they're superfluous. Let's remove them. Okay. And let's evaluate. How you want to do this? You want me to flip first or just multiply in? Multiply in? Can I just please flip first? I might have to do it both ways. Mac, I feel that this one, because we only have the single negative here, might be easier to just flip first. I should have thought about that before I gave you the option. Sorry. It's pretty weird if I just multiply it in. I can do it. I don't have any problem with it, but I think I'm going to lose people. This is equal to 81 y to the negative 8. That just flips to the bottom. Ignore the sign. It just follows, just flips. Over 16 x to the 4 to the power 3/4.
Last time we flipped, didn't you change the sign?
No. We just changed the sign outside. We just changed this sign.
Oh.
I just did that. This says flip the fraction, so flip it. It's not more complicated than that. When you say, but wait, should I change all the exponents that I flipped to? No. Just flip the fraction. Just flip it. When you do that, you're making the common error of, I'm going to try and extend this rule to make it do things that it otherwise shouldn't do. Very common. Don't do that. Try not to. So this is just flip the fraction. Just that negative just flips the fraction. Now, 3/4 as an exponent, 81 to the 3/4. Does anyone know what that is?
1 over 8.
81 to the 3/4?
Oh, 1 to the 27. Or 1 over 27.
No. It's 27.
Oh, well. Oh, because I didn't flip it.
Yeah, that's right. So you still have a negative there. So I take the 4th root of 81. So I take the 4th root of 81. What's that? What number multiplied by itself 4 times? What number to the power 4 gives me 81? Avery? 3. 3 times 3 times 3 times 3, 81. Right? And then I raise that number to the power 3. So that's how people are getting 27 there. If you're wondering, wait, Mr. Jennings, I'm not going to be able to do that on the test. I need some help from my calculator. Then this is what you would do. You would write this as 81 to the 1 over 4 and evaluate on your calculator. It tells you that's 3. Then raise that to the power 3. Y to the negative 8 to the 3/4. What rule do I apply here? This one. Just multiply. Just multiply. Negative 8 times 3 over 4. What's that? What's negative 8 times 3 over 4? Negative 6. Negative 8 over 4 is negative 2. Negative 2 times 3, negative 6. So that's y to the negative 6 over, what number multiplied by itself 4 times gives me 16? 2. Yes, 8 is the answer. And then I raise 2 to the power 3, 8. So 16 to the 3/4, that's just 8. Again, you can break it down in this way. You would have 16 to the 1/4, that would be 2. And then you would raise that to the power 3, that gives you 8. Okay. Multiplied by x to the 4. What's 4 times 3/4? 3. This is x to the 3. If we have 4 pizzas, there's a Hawaiian, there's a pepperoni, there's a veggie, and there's a plain, and I give you 3/4 of each pizza. Count them up. How many total pizzas do you have? Take that fourth 3/4, take 1/4 from each of it, and put them into all the missing quarters of your other 3 pizzas. You got 3 whole pizzas. 3. Or just cancel. 4 cancels the 4 on the bottom, gives you 3. Shani? Yeah. Now, so this is equal to, this is 27. Y to the negative 6 goes to the bottom, so that's 8 x to the 3, y to the 6. Can't be reduced. Okay. I hope that's okay. More questions about this stuff? Avery.
When I did it, I separated this 16 into x4. So it's 16 to the power of 3 over 4.
16 to the power 3 over 4? Yeah.
I'll be right back.
And then I combined 8 and 27.
Combined 8 and 27.
Because when they were combined.
Well, it doesn't reduce as a fraction because they don't share any factors, right? 27 only has 3 as a factor, and 8 only has 2 as a factor.
So I subtracted 8 from 27. I was just wrong.
Subtract. Oh no, because
It would be divided.
it was still divide, right?
27 divided by 8.
It's not like I have. If I wrote it this way, 3 to the 3 over 2 to the 3. Can I subtract these exponents? No. If I have a to the 5 over b to the 5, is that just equal to 1? No, because the bases are different. I can only apply these exponent laws when the base is the same. See? So that's why I can't do any subtraction here. And I can't subtract 8 from 27 to give me 19 because I'm not subtracting, I'm dividing. So it's a different operation. Fraction based on division. Max?
Why couldn't you do 81 to the power of 3/4 in the beginning? Still 27.
It's still 27, yeah. If I did 81 to the negative 3/4
Yeah.
and I just punched that on my calculator, you will get 27. It will output 27. You put that on top of the fraction. If you did 16 to the negative 3/4, then you'll get 1 over 8. That's fine, no problem. But here I'm showing you, this is the y. This is like what's going on under the hood of your calculator. You want to know that. I don't need a calculator to answer this question. Okay, let's keep on going. Now we've got to solve some equations. We had some interesting some challenges about some of these questions. So let's take a look at some of these. Let's zoom in. We'll get me out of the way, as though I could ever truly be out of the way of your learning. And come on over here. So what common bases could I use for this problem? Hayden.
8 to the power of 2, and then 8 to the power of 3.
Yes. Using 8 as your common base is the most efficient. Is it the only choice? No. You could use 1/4 as your base, but it would be very inefficient. Right? So you could use 2 Many people use 2 as your base. That's fine. 8 is a little more efficient, but the algebra is not any harder if you use 2 or if you use 8. Let's use 8 together. So this is 8 to the power 2 raised to the power x plus 7. That's a 2, Mr. Jennings. And this is equal to 8 to the power 3 raised to the power x over 2. Now I multiply these, so 2 times x plus 7 is 2x plus 14 is equal to 3x over 2. I've already gotten rid of my bases because I know that the exponent here is equal to the exponent there because I have a common base. Now just solve.
Wouldn't it be 3x over 6?
Yeah.
No,
Is 3 times
Why?
2?
no. This is 3 over 1, man.
3 times 2?
3 over 1. 3 is 3 over 1. Multiply top times top over bottom times bottom. Right? If I said you have 3 halves of a pizza, how much pizza do you have? 3 halves, right? So it's 3 over 2. So that was a mistake that we were seeing in a lot of places. And this is still just our rule. Multiply, if I have a to the b, then I just multiply. But if they're fractions, I have to multiply them with the correct rules for multiplying fractions. So there, it helps to think of 3 as 3 over 1, because then I do top times top over bottom times bottom, gives me 3x over 2. Now, what should I do? How will I simplify this? There's a few options. Anyone really bothered by that fraction over there? Yeah, you don't like solving it when it has a fraction in it? Am I allowed to multiply both sides of the equation by 2? Yeah, so I can do that. Or so let's do that. This is times 2. And then put this in brackets times the whole side of the equation, other side by 2. Okay. I have to multiply the whole side of each equation by 2 if you want to use that trick. That'll be 4x plus, this is 28. Thank you. I might have made a mistake there. Over equals 3x. There. And now subtract 4x from both sides, and you get 28 is equal to negative x. Multiply both sides by negative 1, and you get negative 28 equals x. Final answer. If you didn't multiply by 2 here, then you would just subtract 2x from both sides. You would have 3x over 2 minus 2x. That's minus 4 over 2x. 2x is the same thing as 4 over 2x. When you're subtracting fractions, you need to create a common base. I'm also, as I go around the room, realizing, ooh, we need to review that. We haven't looked at that for a little while. Adding and subtracting, multiplying and dividing fractions. So that's my fault if you're making mistakes there, because I haven't reviewed it with you recently. I just assume that you remember these things. Okay, so over here, 9 to the negative x plus 3 is equal to 1 over 27x. Hey, Max, were you able to find how to do that with the common base?
Yes.
So what did it look like? Show me, tell me my next line here.
It was 3 to the power of negative 3.
Oh yeah, on the other side?
On the other side.
Yeah, so it's 3 to the negative 3. Notice that 1 over 27 is still a power of 3. It's 3 to the negative 3. Cool, eh? Okay, and then over here we have to the negative x plus 3. Good work, Max. To the x. And then I can just multiply that in, so that's negative 2x plus 6 is equal. Notice I'm doing the distributive property there. Claire? 1 over 27? 1 over 27 equals 1 over 3 to the 3 equals 3 to the negative 1. Negative 3. That's how we did it. That's how Max did it. Maddie?
Would it be okay if you just left it as 1 over 27? Like, what about we couldn't find a common factor? Because, like, when we become hard to find, in other cases,
You might be left with guess and check, or you have to do fancy algebra on this side. You would have to use 1 over 27 as your base for 9, and yes, you can do that, but you would be then raising 9 to a fractional exponent to get 1 over 27, It'd be really weird. It would be 9 to the negative 3 halves. 9 to the negative 3 halves you'd have in there. It's weird. Weird, yeah. Okay, anyway, so that would be like 1 over 27 is 9 to the negative 3 halves. Yeah, so anyway. Oh, so this is negative 3x. So if we add 2x to both sides, we get 6 is equal to negative x. And negative 6 is equal to x. Multiply both sides by negative 1. Helps if I write in my inverse operations, perhaps. Add 2x to both sides. Multiply by negative 1. Both sides. Okay. Boom, 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 boom. We're getting pretty close to the main event here. Graphing transformed exponential functions. Let's keep going. All right, zoom out a bit. So we want to graph these functions. If we have 2 times 4 over 3 to the x. Sorry? Yeah. Mr. Who? All right, let's carry on. We've already started. So we decided on some values for our table of values. And here we're multiplying in. So we have 2 times 4 over 3 to the 1. It's 8 over 3. Calculating 5 is a little annoying. So Cassidy, to answer your question, calculating 4 over 3 to the 5 is a little annoying. I'm not going to do it. I got to think, maybe I can tolerate doing it to the 3 without a calculator. Okay? Maybe even just a 2, and a 2 will give me some information. So let's do to the 2. 2 times 4 to the 2 is 16 over 9. So that'll be 32 over 9. 32 over 9 might look a little annoying. It's bigger than 3, it's smaller than 4. Because 9 times 4 is 36. 9 times 3 is 27. So if this was 27, that would be 3. If this was 36, it'd be 4. This is pretty well smack dab in the middle. So I have this point at 2. 32 over 9 is between 3 and 4. Right there. And 1 was 8 over 3. 8 over 3 is 2/3 bigger than 2, so it's like up there. Okay? And then I'm going to calculate at negative 1. So that would be 2 times 3 over 4. Because 4 over 3 to the negative 1, I just flipped the fraction, 3 over 4. So that's 6 over 4. 6 over 4, 3 over 2. 3 halves. So this is 3 halves, so that's exactly right there. And notice that this almost looks like a line, eh? Maybe because this point needs to be nudged up a little bit more. It's a little closer to 36 than it is to 27. So anyway, it's not a line. So if I evaluate at one of these numbers, I might get where it's going off the graph. And then if I look at negative 5, so that would be 2 multiplied by 3 to the 5 over 4 to the 5. And now I'm reaching for my calculator. 2 times 4. Oh, let's go back here. 2 times bracket 4 divided by 3 raised to the power negative 5. 5 negative. Okay, there we go. Equals 0.474. Okay, cool. So that's less than half. .47. But now sit down negative 5, so it's down about there. Okay, now I've got the information that I need. My asymptote is here at y equals 0. This is the line that the function will approach in negative values of x but never touch. So it's going to look like this. Something like that. Okay, let's keep going. F of x is equal to 1/2 x plus 2. Okay, so here my parent function is x to the 1/2. This is exponential decay, so I'm expecting something that looks a little different. And I can plot right away my asymptote. My asymptote is here at plus 2. That's the line that the function will approach but never touch. When x is 0, this is 1. 1 plus 2 is 3. So that's the point there, 3. Okay. All right. Let's go -1. So 1 over 2 to the -1 is 2. 2 plus 2, 4. And then let's go -3. Okay, let's do f at -3 is equal to 1 over 2 to the -3 plus 2. This is equal to, flip the fraction, 2 to the 3 plus 2. That's equal to 10. 2 to the 3 is 8. 8 plus 2, 10. So that's already off of the chart. So there's 7, 8, 9, 10. Boop. Okay, so this is diving down here. And then let's grab a value like 3. Okay? 1/2 to the 3 is 1/8. 1 over 2 to the 3 is 1 over 8. 1 over 8 plus 2 is 2 plus an eighth. So here's 2 plus an eighth. This would be 2 plus a 16th. This would be 2 plus a 32nd. This would be 2 plus a 64th. This would be 2 plus a 128th. Notice it gets closer, closer, closer to 2. That, what? Sorry, Cassidy? They're not humongous. 32? It's 2 to the 5. Huh? 30, no, 1 over 32. This is when I have x is 5, I have 1 over 2 to the power 5. That's 1 to the 5, which is 1, over 2 to the 5, which is 32. So I have 1 over 32. Very small amount of pizza, right? Pizza was cut into 32 slices, and you got 2 whole pizzas plus one of those tiny slices. Okay? So that's 2 whole pizzas plus one of those tiny slices there. Now, good. Yeah, that's good. And now maybe I want another point in between here to fill in my table. Let's do -2, okay? So if I put in -2 here, that would be 1 over 2 to the -2. That would be 2 to the 2. That would be 4. 4 plus 2 is 6. That point is on the graph as well. Oh. Do I have undo here? No. Doesn't matter. Okay, so this is going to look like this. Get down there, but don't cross the asymptote. That's what it looks like. See, as x gets bigger and bigger, this value gets closer and closer and closer to 0. 1 over 32, 1 over 64, 1 over 128, 1 over 256, etc., etc., etc. It gets so small. But it never becomes 0 or smaller than 0. That's why it approaches the asymptote but never crosses it. Now, this one has a whole heap load of transformations on it, right? So this one, we might create a table of values and then transform the points point by point. Okay? So this is what it would look like. So what are our transformations? What's our A value transformation here? Why does he start with the trick question?
It's half.
No. What's our K value transformation?
0.5.
Yeah, that's a half. What's our A value transformation? 1. Yeah, it's just, there's nothing multiplying here. It's just 1. So we're not even worried about that. Okay, we have a K. We have a C equals -1. And a D equals, oh, sorry. Please add this. Oh, that's going to change everything. I forgot that I had that mistake when I made this. This should have brackets around it. We could do it the other way, but it's going to be much nicer if we... Wait, no, I don't need it. Yeah. If we think about it as transformations, we want to have that there. But if you've already done the work by plugging and chugging, we can create the same thing by... Sorry, my brain is bending a little bit. Let me talk you through as though there were brackets there. I believe I just need a 1 here. No, it should be 4. If you add x plus 2, this should be a 4.
Well, wouldn't you just know that it's gonna be like a negative translation?
If I put the brackets there, yeah, that's 4. Yeah, so that's going to be 4. X plus 4. So with the brackets now, this is x plus 4. So my d is, okay, I don't want to talk about it. Let's just pretend that it's like that. And we'll just do the brackets around it this way. The reason I don't want to talk about it, Mac, is because I'm going to confuse so many people. And it just should have brackets there. We always see the transformations written as k times bracket x plus d and bracket. So the k affects the d. It's about bedmas and it's about the order of things. You can graph the one I gave you. There's nothing wrong with that function, but really to understand it as transformations, I need to bracket that, factor the 1/2 out, and it becomes 4. That's why.
Oh, I see.
Okay.
Okay.
So your function is going to look a little different than my function. It's going to be translated by a difference of 2, but let's take a look at this function here. Okay, so d is going to be plus 2. So my transformation point, xy, would go to, what's going to happen to x? Well, k and d. So I have x divided by k. Otherwise, x values are going to multiply by 2, and then I'm going to add 2 to them. And c values, this is going to affect my y. I'm going to have y minus 1. That's going to be what happens to my points. Okay. So if I want to do this as like a table of values for the parent function, here's my parent function, g of x. It's equal to 1 over 2 raised to the power x. That's my parent function. Then I apply these transformations to it, and I'll get this function here. So to generate a table of values for g of x, let's do x, and instead of here, we'll have g of x. And then in another color, we'll do f of x. Okay. And let's look at minus 4 for x. Minus 1, 0, 1, and 4. Let's take a look at these points here. Let's look at minus 3. Sorry. Because minus 4 is already going to be off our graph. Minus 3 is just barely off our graph. Minus 3 and 3. Okay. So 1/2 to the minus 3, that's 8. Oh, I was going to do that in another color. Okay. This is 8. This is 2. 1/2 to the negative 1, 2. 1/2 to the 0, 1. 1/2 to the 1, 1/2. 1/2 to the 3, 1 over 8. Yep.
I don't. You get that.
I just plug in for values of x here. This is my g of x, 1 over 1/2 x. And that's the parent function of this bad boy. This looks confusing and nasty, and even I made a slight error as I was writing this down for you all.
Does that still work?
This will be the parent function that I can then transform using this idea, point by point. Okay. So, Avery?
So did you just take the g of x equation out of the
Yeah, I look at what's the parent function here. So it's the base raised to an exponent.
So whatever the base is, that's what the equation.
Yep. So let's plot g of x. Well, we've got the pen right. So it's 0 is 1, 1 is 2, negative 2 is 4, negative 3 is 8. Okay, up there. And then over here it's a half, it's a quarter, it's an eighth, it's a 16th, it's a 32nd, it's a 64th, it's a 128th. Right? It's just getting so small, so close to 0. Now I can just transform those point by point to give me f of x. Let's go ahead and we'll just transform those points on our table of values. So here for f of x, I know that I want this happening here. If I divide by 0.5, that's pretty confusing, right? What if I multiply by 2? That's easier, right? So this is 2x plus 2, and then y minus 1. So this point here 2x, so that's negative 6x, plus 2 is negative 4.
Good morning,
And that's y minus
CCI.
1,
Teachers
that's
concerning
7.
the letters A to F may now dismiss students for lunch.
This is negative 2 plus 2 is 0. Oh, weird. And 1. This is 0, 1. So this is 2. And this is 1 is 0. This is 1. 2 times 2 is, this is 4 in the x. And then this is y minus 1. So that's negative 1/2. Then this is 3. So that's 3 times 2 is 6. 6 plus 2 is 8. Y minus 1 is negative 7 over 8. And then I just plot all my points. So here is this point here.
So you're doing something different just because my.
All right, let's carry on. So we'll now plot our points. So negative 4, 7. So here's negative 4, 7. So let's take a look at what happened. This point, it was first affected by k. So that moved it halfway closer. Sorry, it moved it twice as far away from the x-axis. So it moved it over here to that point. So that's k. And then c brought it down by 1. And then d moved it over by 2. You're welcome. And I made a mistake on all these points. Darn. Okay, so I forgot to flip the sign of d when I created this here. This is x plus 2, and we remember that d, we have to flip the sign. So this is x minus 2. This is x minus 2. All of these x values need to have 4 subtracted from them. So this actually wants to go over here to negative 8, 7. Negative 8, 7. This will be negative 2. This is 0. This is 2. And this is 6. Okay, so that's where all of those go. Are you looking for Writers Club? Yeah. It's in 226. I'll be right there. Oh, okay. Lots of mistakes. Oh, I did this wrong again. Oh my goodness, I'm making so many mistakes because I'm rushing now, and because I'm making mistakes because that's what people do. People make mistakes. Notice I caught it. It's embarrassing to make a mistake. I'm a little embarrassed right now, but eventually we get it right. So we're going to get this right, and then we're going to go to Writers Club. It's x minus 2. So negative 3 is negative 6 minus 2, negative 8. Negative 1. So 2 times negative 1 is negative 2. Negative 2 minus 2, negative 4. 0 times 2 is 0. 0 minus 2, negative 2. 1 times 2 is 2. 2 minus 2 is 0. This is our y-intercept here.
Remaining teachers may now dismiss students.
And here, 3, well, 3 times, 3 is 2 times 3, 6. 6 minus 2, 4. Now let's plot these. So now this one goes over here. And this is minus 2. You're most welcome, Max. So it goes here. Okay, it's just off the graph right there. And then this point here, it gets 2 times farther away. That's k. It's times 2. Okay, because I'm dividing by 1/2. So I divide by 1/2. That's multiplying by 2. Goes to there. C brings it down here. D brings it over there. There's that point there at negative 6. I added that point. I don't have that on my table of values. Good news. Okay, this one here, it moves over there by K, moves down here by C, and moves over here by D. Okay, so it's there at the point negative 4, 1. There's negative 4, 1. Here's the point 1. It doesn't move from K, moves down and then over by C and D. So it's there. Okay, we need to just scroll down a bit. This one moves twice as far away, so it moves over there, moves down by there, and then moves over 2. So it's there.
Attention students, Sisters to
That's this
Sisters
point.
Club is meeting in room 130,
This one
130 right now.
Goes over here, down by 1, and over by 2. It's there. Okay. Notice the new asymptote is down here at negative 1. And yeah, the asymptote goes all the way over. So this one, yeah, was down by 2 and over by, that's what that one does. So this is our new function here. There we go. So that's our graph of f of x. We can do it by transforming g of x.
Are you doing Writers Club?
Yes, I am.
There's some people across the road that are across the hallway.
Oh, yes, Miss Burke, is she there, or are you in for Miss Burke?
I'm in for Edward.
Oh, okay. Yeah, me or one of my colleagues will be there just shortly. Just finishing up a video here for my students. So that's how we can take f of x and transform it into g of x to use transformations to graph these functions. Thanks very much, everyone. I hope this was fruitful for your math practice. I learn a lot from making mistakes. It helps me not make the same mistake again. So yes, look forward to seeing what you can do tomorrow on the evaluation of your learning. Bye for now, everyone.